Welcome to another Senior Curriculum Inspiration, proudly supported by Texas Instruments Australia. My name is Peter Fox, and I'll be your host and presenter for this session. The Senior Curriculum Inspiration series is designed to help teachers develop strategies in the efficient and effective use of Texas Instruments calculators through carefully selected mathematics activities, available for free from the Texas Instruments Australia website. Today's activity is titled Vector Graphics, and I'll be using the TI84Plus CE calculator. So, our activity today is using the Cartesian plane in conjunction with vectors. Students will describe points, lines, shapes, calculate lengths, solve problems, and identify patterns. In this first task, students are provided with 3 points on the function y equals 1 over x. Point A has the coordinates -1, -1, point B, 1/2, 2, and point C, 4, 1/4. That gives us position vectors OA, OB, and OC. Now, what's probably a little bit unusual is how I'm going to represent these on the TI84Plus, possibly a reason why we have so many people joining us for this session. I'm actually going to use the y equals editor and matrices. This may seem a little strange, but it allows for quick recall of each matrix and editing, but most importantly, allows the use of variables, allowing us to solve problems. Let me see if I can bring my calculator up, and we'll start entering some of these values. So, you should be able to see my calculator on the screen now. I'm in the y equals editor, just clicking on the y equals button. And to access the matrices within this region, I'll press alpha F3. You'll see my calculator already has a 1-row, 2-column vector ready to go. So I can press enter, and I'll put in -1, arrow across, and -1, and enter, and my first vector is in. That's my vector OA. So I'll continue on, and I'll edit vector OB, which we've got as 1/2 and 2, remembering these points have to be on the function y equals 1 on x. And the last one here we have is 4 and 1/4. So there's our 3 vectors, y1, y2, and y3. When students are going through this activity, I strongly recommend that they keep track of these using a diagram, because they'll be referring back to them all the time. So our first task is to come up with an expression for vector AB. Well, we know from our knowledge of vectors that that would be going from AO to OB, or in other words, -y1 plus y2. I can use my calculator to put those in, negative, and now if I want to recall y1, I can press alpha F4. There are numerous places where you can get the y1 expression from, but here's one of them. So -y1 plus y2. Alpha F4, select y2. Now, just to demonstrate how that's working, I'm going to quit back to my home screen, and I'm going to pick up y4 and press enter. Whoops. That would be negative signs up there. Rookie mistake number 1. Let's fix that. Negative signs. And now let's go back, get my y4. And I can see it's determined the matrix 1.53. What that means in terms of our diagram is if I go across 1.5 units in the positive x direction and 3 directions in the positive y direction, or alternatively, the I and j directions. All right, we can now start entering in some of our other vectors. We've got vector BC. I'm going to put that in y5. So that would be negative of y2 plus y3. And our last one, which is vector CA, I can put that in as negative y3 plus y1. Now, so far, I agree this would have been quicker to do by hand, but bear with us because some of the problems we're going to do in this session end up with some very challenging algebra, which I don't think you'd want to do by hand. So just to summarize, I've got y4, y5, and y6 as my vectors AB, BC, and CA respectively. Now, one of the first questions that the students are posed in this activity, other than just determining those vectors, is what is the sum of y4 plus y5 plus y6? In other words, AB, BC plus CA. As maths teachers, we know what to expect, but let's go ahead and calculate it anyway. y4 plus y5 plus y6. You can see how quick it is to recall those. And of course we get a zero vector because it corresponds to a do-nothing vector. We went from A to B, B to C, C to A. All right, let's have a look at our next question. The next question wants to know the magnitude. And that's where people start to ask, how do I work out the magnitude of this thing? Well, if we know a little bit about matrices, we can multiply them. They need to be in the right format. So let's start. I want to find the magnitude of vector y4, or in other words, AB. So I'll pick it up. Now I know from my knowledge of matrices I can't just multiply it, but let's pick it up. And we need to do something to it, and there's notes on this in the actual activity itself. We go into the matrix menu and select transform. So we've got 11.25. We've still got to do something to that. We know we've got to calculate the square root of that, but you can't calculate the square root of a matrix. And here's the trick. If you calculate the determinant of that matrix, this one here, then it will just return 11.25. In other words, we can calculate the square root of this expression to give us that distance. Now again, you're probably thinking that's a lot of work for one calculation, but rest assured, when you see what's coming up, you'll appreciate how powerful this is going to be. So if we want to calculate the magnitude of BC, we can do it the same thing, only we're substituting in vectors y4, if you like, or equation y4, and also y5. Students are then posed another question, what's the perimeter of our triangle? Now, here's where we can use some tricks. If I go up and get that and paste it down and add on, and I could paste it down again and go back and edit, and that's a little bit quicker. Make sure I'm outside the square root sign, and I'll go up and get another one. Just some elegant copying and pasting here, and we'll put in y6 and y6. And there we have the perimeter of our triangle. Might not be impressed yet? Wait until you see what's coming. Oh, we better save our work. The computer's telling us, make sure you save your work. So let's see, how can we save all of these things? We've got all these expressions built up in here, and we might want to keep them later, particularly as we build more and more vectors on there, which we do later on. So what I'm going to do is I'll quit out of my y equals editor, and under the draw command, that seems a little bit weird, we can store a graphical database. That's number 3. Store graphical database. Where do you want to store it? I'll store my graphical database in graphical database number 1. That means if I clear off all of these equations, recalling that graphical database brings them all back straight away. In other words, all the hard work I've done up here, creating it, gets returned instantly. All right. Now, let's try this. If the perimeter of the triangle ABC equals 17, determine OA. Time for another tip. All right, I said earlier on that we're going to be able to use variables in here. So let's see what happens if I change this, because it says that point A could be anywhere, and I need the total perimeter to be 17. So I'm going to change that to an X, and I'll change that to an X, or rather a 1 on X, and press enter. Now, I want to be able to solve all of that stuff that I did before. So let's just quit out of here. It'd be kind of nice if we could just go copy and paste, but I can't. There's no copy command here. There is one in the program editor, but watch this. I can at least go and get this one, and I'm going to store that, believe it or not, as a string. It's just going to save me a bit of time in a moment. Whoops, it didn't like that. I need some quotation marks. Let's put some quotation marks in here. We'll go and get our expression again and drop the quotation marks in. In fact, let me just test something. This is live. I'm going to test it live. Let's see if we can get that whole expression. There it is. And I'll store that in string 1. Now remembering, and again, this is the clever part. The y equals editor is holding the updated version of all of our vectors. So y4 and y6 are now both dependent on x. So now let's go into the maths solver, the numeric solver, and I have got that in there, but here's how I get that value back. I go second, recall. That's the important part. Got to use the recall, and I'll pick up string 1 and press enter, and it pastes the entire expression straight in. It's kind of like copy and paste. So you've got all those strings that you can use for that copy and paste. Now you see when I go into the solve, it's got x. It's identified x as my variable within all of these expressions. Now I'm going to give it a bit of a clue. I'm going to say I think it's a roundabout. Well, actually, let's go roundabout -3. That's not too far from where x is now. And I'm going to hit solve. It's a soft key. It's the graph key. And it tells me it's at -4.02. That is, in fact, one of our solutions. However, there are 4 solutions. And I'm going to use some nspire software just to demonstrate how that works. So what I've got here is a dynamic diagram, and we can see that if I move it across to about 4 point something, I'm getting, here it is down here, I'm getting something pretty close to that 4 that I got using the TI-84. But what the question is really asking, let me just minimize my 84 for a moment. What the question is really asking is this. I'll draw a triangle. These 2 points are fixed, and I'm just going to put some point out here at random, and I'll measure the perimeter of this triangle. It's 12.6. I'll drag it out until I get about 17. There it is. That's not bad. And then what I'm going to do is lock this up. This is for illustration purposes only. And if you're thinking about this, this length here, AB, and AC add up to a constant amount that is 17 less than this distance here. And by now some of you should be realizing what sort of a shape we'll get if I was to move that point around. Let's drag that point, and I get an ellipse. I'll need to zoom out just a little bit to see it. Zoom out, about here. And then I'll need to just drag that point around again. Oops, I've lost my trace. Let's go back and we'll grab that trace again. So I actually get an ellipse. So I should get 4 points of intersection. I've found this one on the 84. How do I go ahead and find these other 3? Let's go back to our 84 and also the slideshow. The trick here is to change the boundary conditions. I know I've got one at -4, so let's try somewhere between -3 and 0. I'll need to change my guess, or it's going to tell me that I'm a bad guess. And now we'll hit that soft key, solve. The calculator spins around thinking for a moment, and it says there's an error. What didn't it like? Not sure what it hasn't found up this time. Let's just go back. Okay. Probably me typing in a negative sign incorrectly again. Oh, it's found the same one again. I didn't change it. Anyway, we're running out of time, so I'm not going to go back and change these right now, but you'll need to change those according to the possible locations so that the calculator will narrow in, or provide a different guess. So let me just try it one more time. I'll try -0.2 and see if it comes up. There we go, -0.2168. Lucky guess, let's call it, shall we? All right, what about if we wanted to calculate the dot product of AB and BC? How would we calculate the dot product? Well, it's not a lot different than what we've been doing. Let's go matrix. Take the determinant. That just means I'm extracting it out of the matrix. And I want to have Y4. Oh, I know what the other problem is. I haven't put these back to -1. Can't calculate the dot product if you don't have a value in there. I can solve for it. I can solve the dot product equal to 0, which we'll do in a moment. So we want determinant of Y4 times Y5. We need to make sure that we transpose that one. And we get a dot product of 0, which says that those two vectors are at right angles. Students are then asked to calculate the area of the triangle. The next thing they're asked to do is, if C is put to a new location, and here's our example of solving the dot product equal to 0. If C is put to a new location, you notice I've also changed the coordinates of B, so I'll go back into my Y equals editor. I'll update, and this is where it is so good using the equations, because you can see how quick it is to edit all of these vectors, or should I call them matrices. Now what I want to do is solve the dot product equal to 0. I want to find the coordinates of point C that make vector BC and YC into a right-angled triangle. I can go back into my math solver again, my numeric solver. Now, I should have saved my whole expression that I had before, but let's just type it in directly to show you that you can do it straight into this space. I want that one, and I want the dot product of Y5 and Y6. Don't forget to transpose it. And this time, I don't want the dot product to equal 17. That would just be weird. I want it to equal 0. And I'm going to take a guess at 1. Let's see how close we are. It's at 1.73205. That looks remarkably like √3. In fact, the coordinates of point C is √3 and 1 on √3. So, that's another problem solved. That would have been a little bit of algebra. What about this one? Suppose point C is locked out there at 1, 1 now. Point B is still 1/3, A is still -1, and point P is some extension of vector BC. Well, I can do that too. I'll go back to my Y equals editor. I'll change my values here, that being 1 and 1. Then I can quit out of here. Now, if we think about what's going on this time, I need vector BC, or rather the extension of BC, to be perpendicular to AP. So I actually need an expression for vector AP, and I need an expression for vector BP. Well, AP would be equal to A to B, and then some multiple of BC, would get me to P. So I'm going to put that in here in my y equals editor. So remember that vector AB is equal to y4 as displayed on the screen there. So we can put in y4 plus, let's call it n lots, and I'll put in an n. It's the only variable that I've used so far in this one, times vector BC, which we know is stored in y5. And y8 is going to be just my vector BP, which we now know to be just n times y5. So I've got y7 and y8. I want the dot product of y7 and y8 to be equal to 0. I'll go back to my numerical solver, and I want the dot product of y7 and y8 to equal 0. And 0 wouldn't be much good as an estimate. It does actually come up as a solution, but it's not a great one. It's a 0 vector. So I get 1.6. So in other words, if I extended y5 by a factor of 1.6, I'd arrive at point P. Then it says, what's OP? Well, students can work out that as well. And what if AP times BP equals 0 and so on? Now, the last parts of that, I know we've about run out of time, but I really want to show you the next part. Let me just bring up my Inspire software. By the way, that's some of the algebra that 84 is actually solving in the process of doing this problem. So, the last part of the investigation, students get vector OR, BP, BAR, and all of these vectors. So BP down here as an altitude, vector AR is an altitude, and then they want to find the extension of those so that they create a point S. So my altitudes intersect at one point. And the students find this and have a look where that point is. The intersection of the altitudes on my triangle intersect at point S, which happens to be, spoiler alert, on the function y equals 1 on x. All of that done on a TI84Plus CE. Hopefully you've been impressed by this possibility of doing vectors on your TI84Plus CE. Thanks for joining us, and be sure to sign up for more of our curriculum inspirations.